Good evening and welcome, everybody. Welcome back to most of you. My name is Seth McGowan, and I'm the Vice President of the Adirondack Sky Center and Observatory, and your host for this evening's last installment of the Cygnus series for this year. This live and virtual interactive educational presentation has taken place each Friday at 7 o'clock, and all of those are available archived on our YouTube site. And of course, we've done this in order to keep our educational mission going during the pandemic, so that we still have our education program moving forward until we can see you in person again. And we hope to have that happen sooner rather than later. We have started some virtual stargazing. So those will be more in the pop-up vein. Look for those sometimes less than 12 hours in advance. Unfortunately, the sky has been a little bit overcast since we've been able to do that. So we'll be hopefully doing more of that as the winter goes on. For those of you new to the Adirondack Sky Center and Observatory, you'll notice our dark skies position is perfectly suited for astronomy, class 4 Bortle skies, and there's more coming. Our Astro Science Center is under development, and there's lots of interesting exhibits being designed as we speak. This will become an important destination for all ages in the future. And here's a little fly-through of our proposed site. This building is new, and you can see behind it, there's our existing, hang on, it's going to peek up right to the left there in a minute. Our roll-off roof observatory just behind the building. To the left, there it is. Our research-grade telescope, you can see the planetarium on the far side of the building, lecture hall, exhibits, and continuing our hands-on approach to astronomy. All of our exhibits are interactive, and our makerspace will also be interactive, where in this learning lab, you'll be able to engage in virtual reality, telescope making, and many more activities. Our spacious lecture hall will be a great place for large groups to hear about the wonders of space, and our premier state-of-the-art digital planetarium will take you on trips beyond your wildest imagination. So we invite you, as always, to become part of this exciting future and become a member of the Adirondack Sky Center and Observatory, or consider a simple gift to help make the Astro Science Center a reality. If you'd like to talk to us more about those opportunities, I'd be happy to talk to you via email, and I'll provide you with some of those links later. So now on with tonight's show. Before we start, you'll notice that your microphones are muted, and that's to make sure that we don't have extraneous noise from the backgrounds, but feel free to turn off that to enable your microphone if you have a specific question you'd like to ask, or you can type it in the chat area, and we'll make sure that we address that either during the lecture itself or perhaps in the Q&A outside. As I mentioned earlier, our presentations are all available on our YouTube channel, and you'll see this one tomorrow morning before noon sometime, but you'll see a link for that as well. So now it's my pleasure to welcome back to the Cygnus series for the third time this year, the Adirondack Sky Center and Observatory's board member and St. Lawrence University's endowed chair in honor of Henry Priest, Professor of Physics Aileen O'Donoghue, and tonight's presentation, Einstein, Gravity, and Multimessenger Astronomy, Part 3. Take it away, Aileen.
All right, so I'm going to share the screen here and knock you off, and then start my presentation here. And so is it working? Do you see the presentation?
Yes, indeed.
Okay, cool. I chose the right screen. Okay, so welcome back. This is the third of these, because we wanted to make these little shorter talks. So I broke this one up into 3 talks. And so the 3 talks I gave, part 1 was back in August about Einstein's universe and space-time as a fabric. On September 11th, I talked about gravitational waves as ripples in space-time. And the Laser Interferometer Gravitational Observatory, LIGO, built to detect the ripples. And so today is part 3, Multi-Messenger Astronomy. And so, all right, back in August, there was Einstein. And the big ideas, the takeaway were that space is a fabric. It's something, it's not nothing. It's more like a fluid because it's three-dimensional. Gravitational disturbances, just like when you throw a rock in a pond, it propagates, not just on the surface, but down into the pond as well. The gravitational waves propagate at the speed of light, 300,000 kilometers per second, or 186,000 miles per second. And what these are they're the waves in the water. So these are space contracting and expanding. Nothing reflects, refracts, or absorbs them. They just keep going. I'm always pointing out to my students that explosions in space don't stop. They just keep going. Explosions on Earth stop because all the stuff falls to the ground. And they're shaped by the physics that creates them, these gravitational waves. And so they have a particular shape that we can predict from the different disturbances. So that space-time ripples, and the question is, how do we detect the ripples? So we want to detect these gravitational waves. Well, what could we detect? They have to be dramatic changes with large masses. Supernovae, which are giant stars exploding, or massive bodies falling into black holes, neutron stars falling into black holes, or massive collisions, neutron stars colliding, or black holes themselves colliding. And so those two events, those two kinds of massive collisions, we have seen. So on September 11, I talked about gravity. And we looked at, okay, what would a gravitational wave look like passing through Earth? And these are compression expansion waves. And so this is highly exaggerated. But these things are passing through Earth all the time. They pass through your bones are stretching and compressing because of gravitational waves from the other side of the universe. Not very much, but it's happening. And to detect these, they're tiny ripples here on Earth. And so LIGO measures changes in the path length between, it has two perpendicular arms, and it can measure differences, changes in their path lengths down to 10 to the minus 19 meters. That's 18 zeros, a decimal point, 18 zeros and a 1. That's 1/10,000th the diameter of a proton. That's an itty bitty. This is how your bones are getting stretched. But we're detecting these vibrations by these mirrors reflecting light. And there are lots of vibrations. And so the hard work of LIGO that's taken 40 years has been creating the noise canceling headphone effects of canceling the vibrations that surround the detectors, but also the passive damping of all these weights and the way they structured this so that joggers and earthquakes don't jiggle with it, don't make the path lengths change. So we have detected gravitational waves. The first detection was on September 14 of 2015. And then I said, right at the end, the first multi-messenger detection was at 8:41 a.m. on August 17, 2017. And I said, oh, what was that? Well, I'm not going to explain it. So the first what detection? The first multi-messenger detection. So today we're on to multi-messenger astronomy.
Excellent.
So what we've known, the information we've had about the universe, of course, is the material universe. The Earth, of course, there's Mount Marcy seen from Gothics. Moon rocks, we went and got those ourselves. Chunks of meteorites, here, we found those on the ground, mostly in Antarctica, but we can tell they're from meteorites. And then, so other than the stuff we've had, until 2015, the rest of the information we had was from electromagnetic radiation, light. So visible light, radio waves, infrared, ultraviolet light, X-rays, gamma rays. And here is an image from Jet Propulsion Laboratory in NASA, where they show this galaxy, M106, and the white and the gray here, that is, that's showing the URL. That's showing the optical detection. So that's the visible is in white. The radio is this purplish stuff. And so that was detected by the Jansky VLA in New Mexico, where I started my astronomy career. The bluish, this is the X-ray emitting gas. This is million-degree gas. That's why it's glowing in X-rays. It's extremely hot gas. And so that's detected by the Chandra orbiting X-ray satellite. And then the reds are the infrared. So infrared is heat. You can tell the infrared, your burner is heating up because you feel the infrared before you can see it starting to glow. And so in this way, we've had multiple wavelength messengers, but not different kinds of messengers. So what can these ripples teach us? Okay, we've detected a couple. All right, let me do some details about the first detection. So the signal got to Livingston in Louisiana 7 milliseconds before it arrived in Hanford, Washington. The shapes of the signals were predicted by theory. Their theorists have been working. What would a gravitational wave look like if two black holes collided? And this is what they were supposed to look like. And here's Livingston. Here's Hanford. Here's Livingston. And you can see, yeah, there's some noise in the signal, but that's a pretty good match for these signals, particularly, right at the end there. And the calculation showed this was a couple of the merger of black holes in the southern sky. So it turned out it was a chirp. I think somebody asked about this in one of the talks. And so I'm going to play this for you, and it's going to show the signal, and it's going to play twice, and it's going to be at a low pitch. And this was the actual pitch of the signal. This is in time, 0.35 seconds, 0.3 seconds, 0.35, 0.4, 0.45. This frequency of vibration of, a few per second, what's the A note? 440 vibrations per second. And so this is in the range we can hear. And so the first two are going to be in the range we can hear, and it's going to be a thud. I would imagine that a couple of black holes colliding might thud. But then they're going to raise the pitch so that we can hear it more clearly, because it's hard to hear the thud. So let me play it. They'll do the two thuds, two chirps, two thuds, and two chirps. So this is from LIGO. Did you hear it?
Mm-hmm.
Okay, so I had the box checked. Okay, so that's how it sounded. Well, it didn't sound it. This was a vibration. This was jiggling mirrors. So, but if we could have heard it, that would have been that. So what we knew was that, okay, what we know is that on a straight line, if you go from Livingston to Hanford, it takes 10 milliseconds. Well, the difference in the arrival time was only 7 milliseconds. So that means it had to come in at an angle, but doesn't mean it came from the sky. You can take this and it could have come from you. It could have come from the direction of you, as long as it was at this angle away from the line between these two. So actually, there was a whole torus, a whole ring of possibilities of where this could have come from, and not from necessarily from the sky. The gravitational waves pass through the Earth just as easily as they pass through empty space. Earth doesn't affect them at all. And so they did more calculations on it and other things. And so with statistics, they decided they had 90% confidence that it came either from here or inside the purple line, 10% confident it came from in here somewhere. And so on this map of the sky, of course, we can tell the Milky Way galaxy in here. Some other things, these objects, the small Magellanic Cloud, the large Magellanic Cloud, the South Celestial Pole, Canopus, and these are Southern Hemisphere objects. I think that's Southern Hemisphere as well, 3572. But we are familiar with Sirius in the Orion Nebula. All right, so Sirius is up in the morning sky even these days. And so that's the area. But we only had one detector. And if you only have one cell phone tower, it doesn't know where you are. It knows your distance, but it doesn't know your position. You need 3 cell phone towers. All right. And so we knew a direction because we had 2, but we need 3 or more to really pinpoint where this signal came from. And so let me show you what we think happened. It was the merger of 2 black holes. One was 29 times more massive than the sun. The other was 36 times more massive than the sun. How do we know this? Because that gave us the shape of the waves. And 3 solar masses, 3 times the mass of the sun, was converted completely into energy by the event, by E equals mc squared. So if you take 3 times the mass of the sun, which is 1.99 times 10 to the 30 kilograms, it weighs a chunk, and you multiply that by 3 times 10 to the 8th meters per second squared, then you end up with, so 5.4 times 10 to the 47 joules. What's a joule? A joule is the energy it takes me to lift 1 kilogram, 1 meter. So if you have a 1 liter bottle of water, pick that bottle of water up and lift it a meter. That's 10 joules. All right, so you'd have to do that 5.4 times 10 to the 46 times to produce that much energy. If you start now, I don't think you can finish in your lifetime. But in kilowatt hours, which I buy, that was 1.5 times 10 to the 41 kilowatt hours at 6.5 cents per kilowatt hour, which is about what I pay. That's 9.75 times 10 to the $39. Thank God I don't have to pay for it. All right, so how big is that number? Yeah, 1.5, 10 to the 41. These are amazing. If we could grab, a millionth of that, we could supply in Earth's energy needs for forever. See, it's that total energy was greater than the total output of the sun over 4.5 trillion years. It's a huge amount of energy. And yet it was a ripple, a tiny ripple. This happened 1.3 billion years ago when the first fungi were appearing on land on Earth. Next time you eat a mushroom, yeah, its relatives were alive when this merger happened. The merged black hole has a mass of 62 solar masses, so it's a big black hole. So I have this picture in the back with these weird circles. So let's talk about why black holes get pictured this way. When I talked about Einstein, I said one of his predictions of general relativity was that space tells light how to bend, that mass warps space, and then the light follows the warp, and so it bends around mass. And we showed this star, and in Newton's universe, the light from the star would go straight past the sun and not notice the sun was there. In Einstein's universe, it curves. And we follow it back and we say, oh, the star is there. And so the prediction was that if we look at the stars really close to the sun during a total eclipse of the sun, so we can see them, because when the sun is bright, we can't see those stars. If we can see those stars, we can measure their positions. We know their positions really well. Humans have been measuring the positions of stars for thousands of years. Right? We know them. And so everybody ran off to the 1909 total solar eclipse. Arthur Eddington did indeed photograph this. And here are the stars that were moved. They obeyed what Einstein had predicted. It's real, this general relativity stuff. Yes, it's real. The GPS satellites, they're so high above the Earth that time moves faster for them. Yeah, gravity slows time. I had to think a minute. And so this is real. We utilize it every day. And if one of you pulls a phone out of your pocket, yeah, and clicks on your position using GPS, you're using general relativity. Okay, so light coming around black holes can actually go into orbit around it. And so here's a star, and a one solar mass black hole would have a light sphere where light goes in orbit around it at about 4.5 kilometers, 4,500 meters. So light comes from here, goes around, and there is our dedicated observer. And the observer looks at the star over here, but the star was behind him. So as we look at this, the reason we see a black hole as black surrounded by this cluster of stars is because a lot of those star images are from stars behind us, and they've gotten bent around the black hole. And so here's another version of that. So, and I did that explanation so you can understand the image of the merging black holes. And so my background image, I snitched from LIGO from this, an image from this video. So here are these two black holes, one a little bigger than the other. And this video, they are orbiting each other. And as they orbit each other, you'll see these disturbances out here. And all these images are going to warp. That warping of space-time is taking energy away from the orbits of these black holes. So they're going to spiral in toward each other and merge. And then everything's going to be quiet. So watch this. We can play it a couple of times. It's really, really cool. So and they don't really appear to be getting closer. It takes a long time, but you can see the disturbances. That is what's pulling energy out of the system and causing these to orbit closer and closer to each other. And I think they each include images of the other black hole on their far sides. All is quiet. Let me show you that again, and I'll talk less. Just watch. At the end, it happens very quick. And if you look at that signal, yeah, at the end, they get very crowded, and then boom, it's done. And you can see, you know, there's a lot of different institutions collaborating on this stuff. So, in the 1.3 billion years since these black holes merged, life on Earth, remember the fungi were just coming out, life on Earth evolved into plants, fish, reptiles, and mammals that became humans, and my cats that you might hear in the background. In that time, humans discovered gravity waves, built LIGO just in time to see that particular ripple. Cowabunga! That's just so amazing. We, you know, in the time since this happened, we evolved out of fungus. And we built this instrument, detected this ripple. It is just, you know, I tell my students, I say, who needs box wine? All right, speaking of eclipses, April 8th, 2024, I hope you start getting excited now. I'm excited. Another total solar eclipse across North America. We had it in 2017, but look at the path. Shoo-shoom, shoo-shoom, shoo-shoom. Oh my! Look at that. Well, let's zoom in. Almost the center of totality, passing over the Adirondack Sky Center and Observatory. Look at that.
Wow.
Let's pull up the data. So if you just, if you Google interactive map eclipse 2024, you should be able to find this. I did get Hubier's permission to do this. But you can look at this for any location. And so here are the data. But let me blow it up because I can't read that small. We're going to have 3 minutes and 31.8 seconds of totality. 3 minutes, it'll be completely dark. I went, in 2017, I was in Kansas. It was cloudy. It got dark. Night dark. And here, the start of the total eclipse at 3:24:25, the end of the total eclipse at 3:27:57. These are called limb corrections. And what they've done is that the other calculations are for a spherical moon, but the moon has mountains on the surface. And so because of the moon, ours starts 2.5 seconds early, but it ends 0.8 seconds early as well. Hard part is it's on April 8th. Yeah, we're in Tupper Lake.
Eileen, you're fired.
But it'll get dark. Even if it's snowing, it's going to be utterly remarkable. It was remarkable in Kansas. It was dark. Even though I couldn't see the sun in Corona, it's very amazing. And you know, as an astronomer, I'm always wrong about the weather. So I figure if I say in every single presentation it's going to snow, well, it'll be clear. We'll see. 2024, you can start a pool.
We've already purchased shovels and plows.
Oh, okay, good.
Just in case.
And, you know, some mulled wine. Yeah. We'll need it if it's cloudy. All right, so multi-messenger astronomy. What is this? So that was the first detection. That was eclipses. So gravitational wave 170817. So August 17, 2017 at 8:41 a.m. Eastern Daylight Time. LIGO detected a gravitational wave. 1.74 seconds later, the Fermi satellite shown there, it detected gamma rays from a gamma ray burst. 1.7. They hadn't collaborated in 1.74 seconds. I know it's long in computer time, but they weren't in conversation. And Fermi saw a neutron star merger. What they eventually, after everybody observed it, they figured out it was a neutron star merger. And in that neutron star merger, it produced an Earth mass of gold.
Wow.
Gold is really, really hard for the universe to make. And yet, it's really pretty abundant on Earth. All of us have some gold, right? There's probably not one of us that doesn't have something of gold, an earring, a watch, a ring. It's really hard to make it. It turns out that the gold we have is most likely from a merger of neutron stars that happened, and it's explosive and it creates all these heavy elements, and it happened before the sun and Earth formed out of the cloud of debris. If you're wearing a gold ring, just twirl it. That's from the merger of neutron stars. Only 5 billion years ago. Well, 5 billion years ago as opposed to 1.3 billion years ago. So this event was discovered independently from two different messengers, from the gravitational waves and from the electromagnetic waves. The observations followed by more than 70 telescopes, including neutrinos, which are particles, which are actually a third messenger. They're one I was hiding from you. That we receive neutrinos from the sun all the time, right? And so that is a third messenger. So it's multi-messenger. We get particles, we get electromagnetic waves, and now we get gravitational waves. It's a whole new era in astronomy. So here is, so this is the X-ray telescope's image. This is the counterpart of what the gravitational wave came from. And so Chandra, it spotted this little spot, and then it moved into this circle. This circle represents a jet of material coming out of the merger of these black holes, or merger of these neutron stars. And so Chandra initially did not see the jet, but as the jet went out, it broadened because it's running into stuff. And so Chandra was able to see right down kind of the neck. And these gamma ray bursts, these are where, these things happen, and the information, the radiation is sent off in two oppositely directed jets. What are the chances that those jets are going to be aimed at us? Well, they're weeny, tiny. But it happens a lot. So once in a while, it is aimed at us. Once in a while, somebody actually does win a lottery. So that's what we saw. So we saw it in all of these. We saw it in visible. We saw it in X-ray. We saw it in infrared. We saw it in radio waves. We saw it in gamma rays. We saw it in gravitational waves. We saw it in neutrinos. The universe is screaming at us about its nature, its evolution, its origins. Our job as astronomers has been to learn how to hear what it's saying, because it speaks in universes. And we've got to learn that language. It's the most alien language we'll ever try to learn, but we are learning it. Fortunately, it's talking to us all the time. As I tell my students, gravity never forgets. So multi-messenger astronomy. This is the first time astronomers have all of the necessary pieces of information of neutron stars merging from a production of gravitational waves followed by signals in gamma rays, X-rays, optical, infrared, light that all agree with predictions for a short gamma ray burst viewed off axis. That's from the Chandra site. So according to the PI, Daryl Haggard of McGill University, right up here, right up the road, of course the road's kind of blocked right now, but it'll open again someday. This is a big deal because it's an entirely new level of knowledge. This discovery allows us to link this gravitational wave source up to all of the rest of astrophysics. Stars, galaxies, explosions, growing massive black holes, and of course, neutron star mergers. This is really exciting. It's a whole new era brought in that started on this random September day in 2015, and none of the rest of us knew. And we've discovered fire again. So in truth, space-time really is a fluid that ripples. What else can we learn from these ripples? Can they lead us to discovering events that are harder to detect in all of the other messengers? We don't know, but there's a lot of exciting stuff to do. So as always, the adventure continues. All right. Thank you very much.
Thank you. That was absolutely fascinating.
Oh, thank you, Mary. I appreciate the thumbs up. So, yeah, are there questions? Thanks, Gordy.
McKnight has a question.
Yeah.
First of all, thank you, Eileen. You're a rock star. You really explained a lot tonight, and I had a blast.
Oh, great. Thanks, Carl. I appreciate it.
I'm actually intrigued by the idea right at the beginning of Earth doesn't affect the gravity waves, but they affect us.
Right.
And is a good analogy to that radio waves go right through my body and my body doesn't affect them, but they affect me?
Yeah, they jiggle your molecules.
Yeah. And
yeah.
I just find it really hard to believe that the Earth doesn't do anything.
The Earth is a dust mite.
Yeah, but darn it, does my body do anything to those radio waves?
Oh, they're little electromagnetic resonances.
So really, aren't we going to find out 100 years from now that the Earth does affect the gravity, just a tiny amount?
I don't know. It's just not dense enough to really make a difference. It's like, I mean, the other thing about the Earth is that the Earth does not cast a shadow in neutrinos. And maybe I had to do a neutrinos talk now.
I hope so.
Yeah, because these are these little neutrino. It was named by Enrico Fermi, the little neutral one. And so these and physicists invented them because in nuclear reactions, energy was disappearing, and we couldn't account for it. We are so in love with the idea that energy doesn't get lost that we invented a particle to conserve energy, and Enrico named it a neutrino because it didn't carry away charge, and it doesn't have much mass because it doesn't always seem to show up, but it has some mass. And we know it has mass, but we don't know what that mass is, but it's tiny. And neutrinos from the sun are shooting through you, coming up through the Earth from the sun on the other side of the Earth.
Oh, okay.
All right. You got an itch down there? It might be a neutrino. And we are shot through. The Earth is shot through with neutrinos, and the neutrinos don't notice they've been through the Earth. It's kind of like ocean waves. You throw a leaf on an ocean wave, do you think the ocean wave is affected by the leaf? This is the level we're talking about with the Earth and gravitational waves.
All right.
Eileen,
I can hear the doubt, Carl. I can hear
it. You're hurting me. It's okay.
I've got a question, Eileen, that I've had since I heard you talk about this a couple of years ago. The jets that are emitted, why are they? Maybe this is more than this presentation. But why are they jets and not emitted in all directions like a regular explosion kind of a thing?
Because of what neutron stars are. and neutron stars are involved in these gamma ray bursts. And so what a neutron star is, if you take take the sun, it's a normal gas, and it's mostly empty space. So they're, atoms, and mostly atoms of hydrogen zipping around, and there's a lot of empty space. If you start squeezing it and you squeeze the space out from between the atoms, so you've packed all the atoms up as close as they can go, like marbles in a box.
Yeah.
They're held up against each other by their electron clouds, the outer layers of electrons.
Okay.
And so the sun would be about the size of the Earth. That's a white dwarf star. If you squeeze it harder, what happens is that the electrons get force-fed to the protons. And so the proton, when you feed a proton an electron, it loses its charge and it gains a little weight. So it's a neutron. And then you cram all the neutrons close together.
Mm-hmm.
That's a neutron star. And the thing is that when you start out with a normal star, it has a magnetic field and it rotates. Well, and as it's getting crushed, and this happens in supernova explosions, where the layers of the star fall in and crush the inner part of the star into this neutron star state. And as this is happening, the magnetic field is getting very concentrated, and the rotation, just like when the figure skaters pull their skates in, it spins up really fast. So these neutron stars, they rotate, their periods are milliseconds.
I see.
They rotate thousands of times per second, and they're about 10 miles across. So they're barely holding together with their rotation. And so since you have this strong magnetic field and this strong rotation, the only way stuff can get off is along the axes, mostly because of the magnetic field.
Okay.
And that rotation creates these twisted columns of magnetic field. So that's the only way the stuff can squirt out.
Angular momentum.
Huh?
It also conserves angular momentum.
Oh yeah, yeah. The stuff squirting off conserves the angular momentum. So.
All right.
Because it's coming off spinning.
That's a great explanation. I should have asked you that years ago.
Got any other lingering questions?
Who else has questions? I've placed a couple of websites that Eileen referred to in the chat area. So if you wanted to take a look at those.
And yeah, and actually I can put one up. Where if you want, you can snitch these. You can snitch these PowerPoints if you want. So it's on my my astronomy research webpage, and there's a section for the Adirondack Sky Center and Observatory, and I've got these PowerPoints, and so you can go and snitch them if you want. And
very generous. Thank you very much.
I'm really grateful all of you come out on a Friday. Really good of you.
Ethan, is that you?
Yeah. So I would like to know. So if a neutron star, one part can come off, and then another, and then another, and then another, and then another, like, and then there's like little, it's like scattered in little pieces.
Well,
stars break apart.
Yeah.
They don't seem to, because again, they're held together by this this really intense gravity, because they're so dense, and this magnetic field. All these things are kind of holding it together.
So they can explode though?
If they run into something else, they explode, but they don't just of themselves explode. At least if they do so, I don't know of it yet.
Mm-hmm.
So now they're not going to fly apart like, You know, if you spin something too fast, it could fly off into pieces.
Mhm.
Yeah, they're held together. The gravity is just too strong. It's a mega super glue, gravity.
Okay.
I want to put a little shout out there to Ethan. He's been at just about every single.
Yeah, Ethan and Jeff, it's great to see you.
Yeah,
Thanks.
yeah, keep it up.
Yeah.
Could you say something about the work they're doing in Sudbury, Ontario I think it's to detect neutrinos, is it?
Yes. That's a very important observatory. That taught us that neutrinos have mass, and it solved a very vexing problem. Because these neutrinos, these little neutral ones, in the theory of nuclear fusion, we can calculate how many neutrinos are released by the sun all the time, because we see how much energy is coming off from the sun, so we can calculate how many nuclear reactions it has to have, so we can calculate the number of neutrinos. I have my junior physics students do this calculation. It's not very hard. And so they built this neutrino detector in the Homestake mine in South Dakota. They wanted to be shielded from other cosmic particles that are flying through the earth. And so they built this, and they detected 1/3 of the neutrinos that they were supposed to get. And so the experimentalists, they went to the theorists and they said, you guys dropped a 3 somewhere. Go check your math. And so the theorist said, we didn't drop a 3. We didn't drop a 3. You guys, you didn't calculate your experiment correctly. And the experimentalists are like, oh, we were. No, we're correct. 20 years this argument went on.
Wow.
And a new theory emerged that neutrinos came in 3 types. And that one type of neutrino, we know what type the sun produces, and it turns out that these neutrinos, one type can morph into the other types. They can just decay into the other types, but it takes time. And if something moves, if it has no mass and it moves at the speed of light, then it doesn't experience time. Well, whether you have mass or not, if you move at the speed of light, you don't experience time. But if you have mass, you can never get up to the speed of light. And so what they realized was that the Homestake mine detected one type. So they built it in Sudbury, in the old nickel mine. You know, there at Sudbury, Ontario is there because a meteorite clobbered the earth a few billion years ago, and it left a big chunk of nickel, iron nickel, under Sudbury. Nobody would have lived there otherwise. I mean, really. And so they built this detector in Sudbury, and it can detect all 3 kinds, and lo and behold, it detected all of them that the theorists said they should find. Wow. And so the theorists and the experimentalists were correct. They were missing that little piece. So yes, I'd love to go on a tour to Sudbury, but they don't let you into the observatory. It's like, you know, you get a clean environment, you gotta, you know, do all this stuff. But it's very cool. And they do have a great science museum in Sudbury. Oh, so yes, since the nickel's there, it's worth going to Sudbury.
Yeah.
I'd wait for summer.
Yeah. Okay, thank you.
Yeah. Yeah, there's oh, I didn't tell you how we know they have mass. But since these neutrinos manage to decay on their way, on the 8 minutes or more it takes for them to get from the sun to the earth, they experience in time. It doesn't take them on their clocks 8 minutes, but while they move from the sun to the earth, they have time to change type. They have time to decay. So that means they experience time. So that means that they have a mass, but we still don't know what it is. And when I was at the Vatican Observatory, I gave the director the gift of a T-shirt that said, "Neutrinos have mass? I didn't even know they were Catholic."
Try it again, Eileen.
I'm glad you enjoyed that, Carl.
I think that's what my kids would call a dad joke.
Yes. Cool. Other questions, comments?
Yeah, I just find it amazing. I've seen a half a dozen of these presentations on this subject, and I just barely understand what's going on. But I'm just amazed that Einstein 100 years ago predicted all of this.
Yeah, his insight was incredible.
It took him 15 years.
Yeah, I've been at stuff a lot longer than 15 years. Yeah. Yeah. Well, I
But
think he did have a bigger brain. Didn't somebody say that?
But Eileen, also though, you've spent quite a bit of time making those slides and graphics and animations that help us have a chance of understanding it.
Well, I didn't make most of it. I don't make the animations. I steal those from others. But
Well, good for you
I
because
mean, I can make the numbers ripple.
oh, I can't do that. So well done. I mean, those presentations are packed with graphics that give us a hope of following you. So thank you for that extra
Well,
time.
thank you. I appreciate that. Some
need-
of my colleagues think I spend far too much time decorating.
All right. Well, with that, then let me just post one more time our information, our phone number, and email address for contact information, and more importantly, our $15 million capital campaign to build our Astro Science Center here right in Tupper Lake that will accompany our roll-off roof observatory and ultimately research-grade telescope. But that building alone will have all sorts of opportunities. The planetarium, state-of-the-art digital, just a fantastic addition to the Adirondacks, and Tupper Lake in particular. Lecture hall, classroom, and the exhibits that we've been talking about recently are just, no pun intended, but out of this world. So $15 million is a long way to go. If you've enjoyed these, feel free to make a contribution towards that capital campaign. If you know somebody who might have interest in a significant contribution, I don't presume that anybody here tonight does, but if you do, or know somebody that might be interested in a significant contribution towards our Astro Science Center, please give them our information and have them contact us so we can talk to them directly about what that would be. Eileen, again, you know, it's you know, you're an educator. You can tell. That's why that's why the decorations are good. Or they lay.
I'm glad you enjoy them.
Right, we need that, you know. But the third in the series of 3, it all came together in the end. Finally, I know what it means. The multi-messenger astronomy, what that means exactly. So thank you so much.
Well, thank you for all the thumbs up and applause I'm seeing on the reactions. I'm grateful. It's really a lot of fun to do this, particularly since I don't have to give you quizzes, exams, and grades. You know, it's really nice.
And you don't have to grade them either.
I teach for free. They have to pay me to grade. So it's a lot of fun. Thank you, Ethan. And thank you all for coming to these. I mean, it really is a lot of fun for those of us on the other side.
So this is the last in our series. Great way to wrap it up. We will be providing some other lecture type events over the course of the rest of the fall and winter. So if you're not on our info list, use that email address or phone number to get on there to make sure you know when those events will take place. I will be in the position after Thanksgiving, sometime before Christmas, on the Big Dipper, the signpost to the stars. So if you want to know how to find things using just one asterism in the sky, that would be a great place to start. And then we have some others planned for the winter and into the spring. In addition to our virtual live stargazing, which again, looking at the sky tonight, it's not going to happen tonight, but next opportunity we'll certainly do that. And for those of you that have been here tonight and for the past several weeks, thank you so much. I'm so glad that you were able to be here and be part of our Cygnus series of lectures. So thank you and good night.
Thank you all for coming.
Yeah.
See ya.
Thank you.